Bien, ya estamos de vuelta en Siemens Minerals
And
Week.
we're back in Siemens Minerals Week. We're going to continue with the conversation of this Thursday morning. And for this, we have Dan Fodor, head of research and development of Siemens Germany, who will talk about digital twins.
Dan, can you hear me?
Yes, I can
Dan.
hear you very well. Hello, everybody.
Great. Welcome. Thank you for joining us. We are excited to hear about this digitalization process in mining. So we have like 15 to 20 minutes for you. Then we have some space for questions from our audience, okay?
Great. Thank you very much.
Okay.
Thank you for giving me the chance to share with you a couple of issues related to our Siemens digital twin customer experience. I would like to share with you 3 points. First of all, the mining market demand for digital twins. Only shortly then about definition and 2 trends regarding digital twins in mining. And of course, some of the examples that we have regarding grinding mills, belt conveyors, or conveyor lines. And I will close with a short takeaway slide. And I've chosen as motto, like you see in the picture, the fact that indeed the real world and the digital world are getting closer and closer. And in my opinion, this is valid also for the mining industry. Which means the real world is, of course, made of the mine processes, of the mine machines, applications, assets, while the digital world is mainly consisting of digital twin of the same, of processes and of assets. Okay, that's very good. And we trust we can use the digital twins in order to empower our partners, our customers to master as good as possible their digital transformation and their sustainability challenges. And now about the demand from the market, from the mining market for digital twins. There is a lot, I could say each day an increased demand about this kind of solutions. I selected only 2 of them. One is related to Anglo-American. You can see a sketch which the CEO of Anglo presented in May this year. And this clearly shows the expectation of Anglo regarding the digital twin concept. Of course, here we have a picture about, let's say, a machine. It could be a lubrication system. It could be also a mill, whatever. But it's clear the expectation is there about digital twin and the benefits digital twin should bring for the mine. And on the right side is an official inquiry of Codelco end of 2020 about digital twin for conveyor belts. So these are only 2 examples. I'm sure you know many more of them, but I hope we all agree the demand of mining industry for this kind of solutions called digital twin is undoubtful. And now what is different from one inquiry to the other is the understanding behind the digital twin, the expectation to the digital twin. That's why I would like only shortly to share with you a definition. On the purpose, I took a general definition and let's say public definition from Wikipedia, because there are the 3 major topics here regarding the digital twin, and they fit very well to mining in my opinion. So a digital twin can be used for monitoring, diagnostics, and prognostics in order to optimize the performance of the asset and its utilization. The data from sensors can be combined with historical data of the asset, can be combined also with human expertise and with the simulation learnings in order to improve the forecast, in order to improve the outcome of the prognostics. Hence, the complex prognostics and the intelligent maintenance platforms rely on digital twins to find root causes of problems and to, in the end, to improve the productivity. This is the utmost goal for the use of digital twin. And it is a common opinion today that the digital twins are permanently gaining importance. This is valid also for mining. And I would shortly sketch only two trends. The first one is the combination between simulation models and artificial intelligence, because the core component of a digital twin is a simulation tool. But it is expected that simulations use more and more artificial intelligence for the simple reason that a lot of systems, a lot of components cannot be completely described by mathematics. Hence, the digital twins will integrate more and more simulation and artificial intelligence. In this sketch here, you can see this is the whole area for machine simulation, and this is the neural power unit, if you like, but this is the AI. It's not significant whether edge-based, local-based, or cloud-based, not the algorithms, but the combination between simulation and artificial intelligence within digital twins is a clear trend. The second one, the digital twins will definitely gain more and more trust in the near future. I would like to make a comparison with the navigation systems from our cars today, which we use, I allow myself to say, it's also my case, without thinking, because they are convenient, they are reliable, and we trust them more than any local person that we would ask about a target, about a goal. So in the same way, the simulation models are currently quite wide used in mining for design and validation of industrial systems. And soon we will have enough validated systems, if you like, enough references, so that the trust of the digital twins will be undoubtful. So the second trend is that after a clear and necessary validation for each and every project, for each and every process or asset, the digital twins will be highly trusted. And there is also a very strong opinion that the decisions based on digital twins will soon be more trusted than the decision taken without the contribution of a digital twin. And now to the example, let's get a little bit downwards to some examples closer to the technology for a grinding mill, for a belt conveyor, and the whole conveyor line. Let's start with a grinding mill, a gearless mill. We have here some picture of a digital twin solution for a gearless mill drives driven mill with the key statements to which the digital twin offers answers. The key questions: how is the actual status? For example, what is the stator alignment situation, the air gap situation currently? How do the transformers, how does the e-house operate? We use artificial intelligence for detecting anomalies in this component within the digital twin already. Understanding what's happening, status, for example, of the lubrication system of the mill bearings. We use AI models to understand, to analyze the flow of the oil, the accumulator pressure, the pump activation frequency, pump active duration, and so on, to understand, is the lubrication system doing the right job currently or not? So clear statement, we already have artificial intelligence integrated in the digital twin of the gearless mill in this case. And to be more specific, you can see here the same questions with a picture, a look and feel of our digital twin solution and status overview. You can see here these red spots are the abnormalities detected, the changes, the deviations from normal operation detected by the AI model. And here the same AI technology for a temperature model this time to show whether the temperature, for example, in a winding of the motor is within the tolerance or not. What is important also in these pictures here is that the maintenance operations do have a very important role within the digital twin. And The specific experience from site can be implemented into the digital twin, enriching this way the functionality of the digital twin and making it not a solution from the shelf, but a solution which is focused on the very existing mill in the mine site. Second example related to a belt conveyor. By the way, this is an operative project going live, being commissioned within this year. So the digital twins are here in the mining industry already. So we have, of course, a real conveyor, which is very interesting because it has a very strong belt, one of the strongest worldwide. We have the simulation model sketch here. We have to define the interfaces here, where you see these forces to implement it within the digital twin. We have to strongly validate it. You have here only a selection to see how accurate this validation process is. And then you have, in the end, a digital twin able to operate in real time, which means able to show what's happening and able to compute forward to forecast what will happen given the actual state point. With this, one of the major benefits is, for example, that based on the digital twin, we can investigate the drive and the control effects on the mechanics and on the belt. Of course, you know what for issues can be generated in these elements. And savings through shorter on-site commissioning is another benefit. Now, the second example related to the belt conveyor digital twin is understanding the root cause of an incident, a failure, which happened at a given moment in time. With the digital twin, we have the chance to virtually reproduce what happened, 100% accurate, because the digital twin is validated. Then we can understand the evolution of the parameters, we can understand the sequence of the events and the true root cause. With this, we can understand what actually happened and we can prevent it happening in the future. For example, let's say we have a conveying jam in the discharge area of at the discharge pulley of a belt conveyor. Then, of course, the accumulated material down there breaks the belt. The drive station does not know this and it continues driving, pulling the belt. The belt is pulled out of the tensioning station somewhere. And then, of course, we have a belt thrown out or deformation. We have dropped material from the belt, damaged idlers. And I'm sure those of you operating in the mine know better what this means. All this can be understood virtually and hence prevented with the use of a digital twin. And the last example from my side, the transportation process, or if you like, the conveyor line. You have here an example. It's not exactly the one we mean. It's an overland conveyor, eventually some crushers up front. This is the transportation process, and the digital twin of this transportation process includes functionalities like I pictured here, like simulation models already meant, like the situation of the components. We call it health situation, health status, computation and monitoring of the key performance indicators, event, not only event analysis, but event classifications, what happened when, due to which cause and to which chapter the event belongs, then identification of the downtimes and what we call an operation database, for which I spent almost the last slide of my presentation. We call this operation or know-how database in the case of the belt conveyor. This is a collection of information based always on 3 pillars, which is the root cause, which are the countermeasures, and what happened basically. So for example, for the failure mode misalignment of belt, we can have several root causes. And then the user of the digital twin can see, okay, a possible root cause is that material is not fed in the center of the belt. Okay, what should I do? Change the conditions in the feeding station, and at least he has a fast help what he has to check in order to prevent that this failure mode is going worse. Very important here, this database, it has a collection, a multiple collection of data already but it can, for each and every asset or process, it can be enriched with specific experience from that asset or from that process. With this, to the last slide, takeaways under the motto, our Siemens Digital Twin Customer Experience. Indeed, so the mining demand for digital twins is undoubtful. It ranges from single machines like mills, like belt conveyors, up to entire processes or mines. The digital twins can be used to optimize the performance and the utilization of the respective assets. Within a digital twin, sensor data are combined with historical data and, very important, with human expertise and simulation. Based on complex prognostics and intelligent maintenance solutions, the digital twin can improve productivity, can support decisions which lead to the productivity improvement, and our Siemens digital twin-based solutions for mining, they can as well be integrated in the company's ecosystem in what's existing, and they can, of course, as well integrated in upper level Siemens solutions like the digital mine solution, like stockyard management, like manufacturing execution system solutions from us, and so on. So indeed, the real and the digital world are getting closer and closer also in the mining industries. Thank you. With this, I look forward to your questions.
Thank you, Dan. Thank you for your keynote. We have some questions for you, of course. First one says, as it goes, what are the factors for the selection of a platform for the implementation of a digital twin? For instance, MATLAB or Simulation X, says the question.
Okay. Very good question. Thank you. It depends on the experience. We indeed use these software platforms because we find them, first of all, attractive because they are made. Okay, the MATLAB Simulink, it's one very traditional simulation tool, but the Simulation X is a software platform developed by mining users for mining users, and this was very important for us to ensure that we have an intuitive use of the solution in the end if it's based on these platforms.
Okay, thank you, Dan. Next question says, what kind of professionals are involved in the construction of a digital twin?
I would sketch at least two kinds of professionals which are very important. Of course, on one side, the IT professionals, the guys that take a lot of data and build in the end a simulation model, validate it, and at a certain extent release the model as validated online or offline. But the same important is the profile of a mining, let's say a mining specialist, a mining user of the assets in mining, that a user that knows the processes and knows what happens in the mine, so that we can combine. The digital world offers fantastic potential, but we have to map it to the reality in the mine. And that's why the second profile that I see as very important is a guy with significant experience in the mine site processes and machines.
Okay, thank you, Dan. The third and last question is, according to your experience, what is the expected payback time for a digital twin project?
Very good question. I have to answer it very general because, of course, this depends. This payback time is different for example, for a grinding mill, is different for a belt conveyor, is different for a conveyor line, and is different for a stockyard management system for a digital twin of the respective stockyard. So I would lie if I would answer it's very fast, or it's 1 year, or it's 5 years. It depends from case to case, but there are for sure arguments which entitle the statement that there is a return of investment which makes the the work with digital twins very attractive.
Dan, thank you very much for your time, for sharing with us your thoughts and inputs about digital twins. I hope you enjoy your time too. Thank you very much.
I did. Thank you very much. Take care. Bye-bye.
Bye. Have a nice day. Bye.
Have a nice day too.